Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Maya Fishbach with us today. Hey, Maya.
Hi, thanks so much for having me.
Well, thank you so much for agreeing to talk about your very lovely APJ letter. I think that's pretty awesome. Maya, where are you located at?
I'm in Chicago right now.
Chicagoland. Let's see, it is June 21st, 2022 as we shoot this. So it's solstice. Hey, how about that? We get to shoot on solstice.
Yes.
I would imagine Chicago is in full bloom in its summer.
Yes, I think it's going to get to 100 degrees today. We really don't deserve it after how cold it's been this winter. We deserve to have some mild weather, but we're not getting it.
Well, Chicago struck me as like, it stays cold for a long time, and then all of a sudden you have the power switch gets hit, and it completely shifts inside of about a week. And backside into fall, it kind of does the same thing. So yeah, and that means the humidity is probably up in Chicago as well too. So it kind of comes with the territory.
Yeah.
Yeah, very good. What's your position there? Where are you at? You're at Northwestern, yes?
I'm at Northwestern. Yeah, I'm currently a postdoc at Northwestern.
Very cool. Awesome. Very good. 100. I'm in Phoenix, and we'll probably definitely clear 105, 106 today. I haven't looked, but we are in the thralls of summer as well. So solstice day.
Yeah. Yeah, first day of summer.
Official.
Yeah.
Very cool. And Maya, what do you like to do for research?
Yeah, so I like anything to do with gravitational waves, mostly thinking about the astrophysical interpretation of gravitational waves that have been detected by LIGO Virgo COGRA, so the ground-based gravitational wave detectors. We've detected dozens at this point of binary black holes, some neutron star black hole systems, and some binary neutron stars. So merging compact objects. But yeah, that had gotten me generally interested in compact objects, even though I came in from the gravitational wave side. I was like, oh, hey, there are other astronomers who are thinking about compact objects too. Who knew? Just kidding. But yeah, so then I started thinking about, how can we kind of combine knowledge across different observational strategies like gravitational waves, and then thinking about the stellar mass black holes that we know about from X-ray observations, like the black holes in X-ray binary systems. So yeah, that's what brought me to thinking about and writing this paper.
Very cool. Very cool. And that is going to bring us to this very awesome APJ letter. Apples and oranges, comparing black holes and X-ray binaries and gravitational wave sources. And Maya, take us away.
Yeah. So I guess the title describes the paper, nickname Apples and Oranges, because you think like maybe I shouldn't compare these black holes in these different types of systems, like they're pretty different from each other, but you want to do it anyway. So let's try to do it and see how far it can take us, I guess. So yeah, the reason that we want to think about these black holes in different systems is because black holes are telling us about massive stars. They're the end states of these massive stars. Massive stars are super important inside their galaxies. They have these really large effects, but they're pretty short-lived and rare. So we try to study them in every way we can. And the black holes that they make stick around forever. So we can look at these stellar skeletons to learn about stellar evolution and the evolution of these systems. Nice. And so, yeah, so there are different systems that we know black holes to live in, that most of them that we know about right now. So talking about stellar mass black holes, like masses less than 100 times the mass of the sun. Most of them are in these gravitational wave binaries, in these binary black hole systems. So two black holes that are merging. Each gravitational wave event gives us two black holes. So that's great. Then there are other systems that we know black holes to be in. And for this paper, we're focusing on black hole X-ray binary systems. So my co-author, Vicky Calagera, who's a professor at Northwestern and actually the director of Sierra. So she's done a lot more thinking throughout her career about black holes and other types of systems. This paper was kind of my first time thinking about X-ray binaries at all. So it was fun to learn stuff. Yeah, there's also, so here this paper is focusing on binary black holes and X-ray binaries. There are also black holes that have been observed in other systems, like in non-interacting black hole systems where you see the radial velocity of the companion star, as well as the microlensing observations of like truly isolated black holes. And so those are growing populations that we are so excited to add to the family.
Nice.
Yeah, but getting back to this paper, so we want to compare these black holes. Like when we observe black holes, we get their masses and their spins, sometimes both, sometimes just one. And we want to kind of think about, okay, what are the masses of the black holes in these different systems? Are they similar? Are they different? But that comparison is difficult because they are in different systems. And so there might be two types of selection effects. There are astrophysical selection effects, which are like some black holes might only be found in high mass X-ray binary systems, but then they may not evolve into merging binary black holes. And some merging binary black holes may have been assembled dynamically and never even passed through like a high mass X-ray binary phase. So there's like kind of these astrophysical selection effects, and there are so many uncertainties in the evolution of the different systems. And then there are the observational selection effects. And those are like where we only have the samples that we've detected somehow. Some systems might be easier to detect than other systems. So this paper is kind of like a very simple first pass. So we're ignoring astrophysical selection effects. So kind of the differences that we get out in the comparison are possibly hinting at those astrophysical selection effects. But we're also ignoring observational selection effects in the X-ray binary population, because those are also difficult to model. We're including observational selection effects in the gravitational wave population because those are just super easy to model, because the gravitational wave signal directly depends on the masses and spins of the two black holes. And in the X-ray binary case, those observational selection effects depend not very indirectly on the masses and spins of the black hole. So no one has like a complete model of that. Yeah, so I guess those are just some caveats to put out of the way first. Yeah, but we can get to some of the results now. Guess we can start with table 1. So if you want to, I guess, look at this data for yourself, in this table lists the data that we used on the X-ray binary side. So split up into the high mass X-ray binaries, those are the top 3, and then the low mass X-ray binaries are everything else, and listing the black hole masses and the black hole spins. And all of this data was gathered by some amazing observers, not me. So very grateful
very
for
good.
people who've done these measurements. And then we're using data on the gravitational wave side, which is available in the gravitational wave transient catalogs, GWTC. Here we're using GWTC2 from the LIGO Virgo collaboration. There's been an update since then, which is GWTC3.
Okay.
Yeah, so I guess we can move to the first figure.
Okay, and there's our awesome observer.
Yeah.
Figure one, CDF.
Yeah, so the rest of this paper, we're basically first comparing the masses and then comparing the spins, trying to see, are they the same, are they different, and what is that telling us? So
Okay.
figure one is focusing on the comparison between the masses of black holes and the gravitational wave sources and the masses of the high mass X-ray binaries. So starting with that purple curve, yeah, the steps, those are the primary masses of black holes in binary black hole systems. There are 44 masses there, and those are like the events that we've observed, and this is just a cumulative distribution function. So you can see, for example, like at CDF of 0.5, that's the median mass in our sample. It's like 35-ish. So we're observing pretty massive black holes and gravitational wave sources. But this is where the observational selection effects come in. So part of the reason why these black hole masses are so heavy is because we're biased in gravitational wave detection towards detecting big black holes. Those black holes that are bigger are emitting louder gravitational waves. So we can correct for those observational selection effects and fit for the underlying astrophysical population of merging binary black holes. And that's what you get if you move from purple to that green unfilled band there. Right. Yeah, so you can see that even though our median observed black hole mass is like 35, the median astrophysical mass correcting for those selection effects is like 10-ish, 12. Right. Yeah. So, okay, so that's what you get there. So now we've corrected for selection effects, but then we want to compare this to a sample of 3 black hole masses in high mass X-ray binaries. And so what we're doing is let's draw 3 events from that green distribution. And when we get that, we get the orange band. So lots of uncertainty. That's from the counting uncertainty because we're only drawing 3. So basically, if those 3 masses could be lots of different things because there are only 3 of them drawn from this green distribution. Gotcha. So now we can finally compare that prediction in orange from the gravitational wave observations to where those 3 black holes would lie against the blue. And those are the actual observed masses of the high mass X-ray binaries. Gotcha. You can see that they fit comfortably within that prediction. So there's no real tension, even though first glance, you're like, oh, these 3 high mass X-ray binaries, the heaviest one is like 21 solar masses, whereas we observe so many binary black holes that are 30, 40 solar masses. You think on the surface, like maybe there's some tension there, but there actually isn't if you account for those gravitational wave selection effects and this small sample size uncertainty.
Cool. I'm with you. Good.
Yeah. Okay. So then figure 2 is doing the same thing for the sample of low mass X-ray binaries. So the difference here, so low mass X-ray binaries, their companion stars are much lower mass than in the high mass X-ray binary case. And there are way more of them that have been observed. There are like 20 here. So we can do the same thing, but now instead of drawing a prediction of 3 black holes from the gravitational wave side, we can take 20 black holes to compare against the sample size of 20. And so that's what you have in orange. Here, that's the prediction from the gravitational wave side of 20 draws.
There you go.
And so you can see that here is like the median is around 10, which is what we had in that green curve above in the underlying astrophysical population.
Yep.
Yeah. And then if you compare that against the low mass X-ray binary observations, which is in pink there, you can see that they are much lower mass than the black holes and gravitational wave sources. So like the maximum one is 10.
Right.
And so on the surface, there's definitely tension between these mass distributions. One reason is we know that they're different astrophysically. Low mass X-ray binaries are never going to evolve into binary black hole sources because their secondary stars are way too light. They're not going to become black holes. But one way to maybe think about it is that there's this hidden variable here, which is that companion mass, right? So binary black holes, there's always two black holes. They have some companion mass, and low mass X-ray binaries, those black holes have some companion. On the binary black hole side, we know that there's a correlation between those two masses in a binary. And so maybe the fact that low mass X-ray binaries, those black holes are skewed to much lighter masses is actually because their secondaries are so light. And so if we take the gravitational wave population prediction, but now condition only on those black holes that have light companions, and in the gravitational wave case, we can't go down to very light companions. So we can just sort of cut the sample at like 8 solar masses, which is light for the gravitational wave case. Yes. But you can see that if we do that, then the black hole primary masses that we predict are much lighter. That's what's shown in green there. Yeah. And so it definitely moves things more in the direction of the low mass X-ray binary observations, which is to say that maybe this correlation with the companion mass is explaining this difference to some degree.
Cool. I'm with you. Yep.
Yeah. So yeah, so that's pretty much what there is to say about the masses of black holes in the different systems. Like, they're actually not that different, and maybe any difference can be explained by just this companion mass. So yeah, so then the next set of figures are about spins, where things are more complicated, as I guess always for black holes, spins are harder than mass. So I guess moving on to figure 3.
Okay. Yeah, black hole spin. Okay, I'm good. Okay.
Yeah. So now we're talking about the spin parameters of black holes. So this is this dimensionless spin magnitude that's always between 0 and 1 for black holes, and we can look at the measured spins of the black holes in the different samples, and here we're fitting that to some distribution. So there's in orange there are the spin magnitude distribution for binary black holes. That's taken from a fit by the LIGO-Virgo-Cogra collaboration. The model that we're fitting here is a beta distribution. Okay. And I've just showed the prior here in black, which, just to clarify, that the model that we've chosen is having some effect on, what possible distributions are allowed. We can't have things that are too sharply peaked at 0 or too sharply peaked at 1 just because of the model. So just to kind of be straight up about that effect of the model. But saying that, the binary black holes, you can see, have very small spins. So fitting this model to the spin magnitudes, they're usually around 0.2. They're almost always less than 0.4. We don't see rapidly rotating black holes in the gravitational wave sample,
Right.
which is a big contrast from the X-ray binary sample.
Yes.
So both low mass X-ray binaries, which is shown in pink, and high mass X-ray binaries, which are shown in blue, have
Right.
much larger spins, where the
Indeed.
median spin in this population here is like 0.6 and above. So you can see there's the spins of black holes in high mass X-ray binaries and low mass X-ray binaries are consistent with coming from the same distribution. So the pink and blue overlap, but there's no overlap with the orange. So very different spin magnitudes in the gravitational wave versus X-ray sample.
Yep.
So then, okay, so maybe we can try to understand this a bit more, which is what the next few figures are looking into. So in figure 4,
there is our
we're
sorry, I'm looking at your beta.
Yeah. Yeah, so in figure 4, we're trying to fit a different distribution. And the goal here is to tease out, like, okay, maybe not all black holes and binary black holes have the same spins as black holes and X-ray binaries, but maybe there's a subpopulation of binary black holes that have similar spins to high mass X-ray binaries, which we think that some binary black holes have evolved from a high mass X-ray binary phase, and not much can happen to the spin of the black hole. So we kind of think that, you know, there should be at least some binary black holes that have similar spins to the high mass X-ray binaries. At least, like, both of those black hole spins are thought to be the natal spins of the black hole, so the spins that they're born with. So yeah, so let's try to find maybe a subpopulation of binary black holes that have spins that are as rapid as the high mass X-ray binaries.
Okay.
So to do that, the earlier figure was fitting this beta distribution to both component black hole spins in the binary black hole, assuming that those two spins are independently drawn from the same distribution.
Yes.
Here, we're trying to put as much, we're trying to make the model as flexible as possible to maybe contain this subpopulation of very rapid spins. And so what we're doing is so the background to this is that the spins that are measured in gravitational waves, there's really this one spin parameter that we measure for these 6 degrees of freedom, which is the 3 spin components for one spin vector for each black hole. We measure this mass weighted average of the spin component that's aligned with the orbital angular momentum. So that's this Z projection here. What's shown here in this plot is the primary spin, so the spin associated with the more massive black hole, A1, and the component of that that's projected along the Z-axis, which we use Z-axis to mean the axis of the orbital angular momentum, so perpendicular to the plane of that orbit.
I'm with you.
So by what we're really measuring well with gravitational waves is the average of this A1Z with A2Z weighted by the masses M1 and M2. But we're trying to dump as much spin into A1 on a population level as possible. So let's just assume that A2 is always 0. The secondaries are non-spinning.
Okay.
So that's the population model here.
All right.
Assuming the secondaries are non-spinning, and then let's fit this primary spin component that's aligned with the orbital angular momentum. And let's just assume that there is some subpopulation that's sharply peaked at 0. So that's a spike here that you see at 0 is just kind of a model assumption. We're assuming that this primary spin is a mixture between this near 0 component and this wider, possibly higher spin component, because we're trying to see how big this higher spin component can be. And so what this plot is showing is that inferred population distribution, the posterior or the probability distribution function on the y-axis as a function of this primary spin sub z. And in orange is the fit to those binary black holes. So again, we see the same idea as figure 3, which showed that binary black hole spins are small. And this is another way of seeing that. We see that like there's a lot of support near 0, and then this other component that we've put in that can go to very large spins still only peaks at around 0.2 and really dies off by 0.6.
Yeah. Yes.
Yeah, so contrast to that with the spin distribution of the high mass X-ray binaries, which is shown here in this navy blue color, which is skewed towards very high spin. And now we can play another game to see how consistent we can make these distributions, which is here we're showing the spin component aligned with the orbital angular momentum, but it's possible that in the high mass X-ray binary case, you have your black hole spin that's nearly aligned with the orbital angular momentum. But then after the second star explodes and becomes a black hole, that can tilt the plane of the orbit. And so impart so the final spin of that black hole would actually be tilted. And so it wouldn't all be pointed up and on the z-axis.
Got it.
So we can take that blue distribution and apply some distribution of spin tilts to it. And if we assume those spin tilts tend to be pretty small, which is here in purple, so we describe that spin tilt distribution by this sigma of cosine of the tilt, which is the angle between the final spin and the orbital angular momentum axis, or the z-axis. We assume that is 0.2 radians, or like 37 degrees. Then we can move that blue distribution over to have more support at smaller values. If we assume larger tilts, which is shown in the green, unfilled distribution, we can move it over to have even more in the direction of the binary black hole case.
Got it.
And then this brings us to figure 5.
Okay. There's our beta distribution. 5. HMB like. I like that.
Yeah. Yeah, so figure 5 is the next part of this story, where we've really tried to see, okay, how much can we push this binary black hole spin distribution? How much can we push the high mass X-ray binary spin distribution to make them have the most overlap? And so this overlap is a spinning HMXB-like BBH fraction, which is what fraction of these binary black holes can be spinning like the black hole spins in the high mass X-ray binaries.
Yes.
So if we assume there's no tilts at all, we have this blue unfilled distribution where we can say, okay, like 10% of binary black holes are possibly spinning as fast as the high mass X-ray binary population.
Okay.
As we allow more and more tilts, that becomes broader. We can allow more of those binary black holes to have spins as high as the high mass X-ray binary, simply because now those high mass X-ray binary like are not all in the z direction, where we've constrained things to be small. So then we can move things to maybe be as high as 30%. And so this 30% is kind of our conservative upper limit. Like
Okay.
The main conclusion being spins in binary black holes are very different from spins in high mass X-ray binaries, but maybe 30% of binary black hole spins have spins as high as the high mass X-ray binary population.
Cool. Okay.
Yeah, so then the last figure is figure 6, which is also talking about spins. But now this is kind of touching on a suggestion that people have had in the literature for like the past couple of decades, is that the spins that we observe in black holes and low mass X-ray binaries might not be the spins those black holes are born with. It might be spin that they gained by like during the accretion process, like they're actively accreting material from their donor star. Maybe that is also spinning up those black holes.
Yep.
And so we can ask, well, how much spin are they gaining? And so the answer is different whether you believe that the natal spin of those black holes is described by the gravitational wave spin measurements or by the high mass X-ray binary spin measurements, because we usually, in contrast to LMXBs, we think that the black holes and gravitational wave sources and the black holes and high mass X-ray binaries don't really have a lot. They don't have enough time and they're not accreting enough material to really change their spin. So we think that in both of those populations, that really is the natal spin of the black hole. So if we assume that the natal spin is described by the gravitational wave spin distribution, we get this pink curve here, which is always bigger than 0. Like we think if this is the case, then low mass X-ray binaries have to be spun up by accretion like in 90% of times, or 91%, at least 91% of the time they must be spun up. On the other hand, if the natal spins are described by the HMXB distribution, then there's no room for spin up by accretion. We constrain it to be this blue curve that's tightly peaked around 0. So again, this is just to say that the spin magnitudes and low mass X-ray binaries and high mass X-ray binaries are consistent with each other, but not with the gravitational wave population.
I'm with you. Yep. Very cool.
So that's those are pretty much all the results in the paper. So there is some discussion at the end that's summarizing the results and then trying to make sense of some of it, or also summarizing some of these open questions. So the main results are that the masses, there's no real issue. Things seem pretty consistent for the black hole masses in these different systems, once we account for those gravitational wave selection effects. On the other hand, the spins are pretty different.
Right.
And so there might be some issues there, like, okay, one is measurement uncertainty. Do we really trust the spin measurements of black holes in these different systems? I think we trust them enough for these main conclusions to hold. Also, it's more fun if there's something that's going on that's not just like systematic uncertainty.
Indeed.
But
it's all
but there are some other possible explanations for these discrepancies, which are explained here in the conclusion. Like maybe the natal spins of black holes has something to do with the supernova explosion mechanism, which we know depends on masses of stars and the masses of those final black holes. So maybe there's some correlation between spin and mass that could explain some of this. And then there's the selection effects that we haven't treated at all on the X-ray binary side. And so it's possible that we're observationally biased towards detecting rapidly spinning black holes in X-ray binary systems. For some explanations have been put forward in the literature for that, like maybe rapidly spinning black holes are more likely to form accretion disks that lead to longer and brighter X-ray emission. Maybe there's some correlation between the period of the high mass X-ray binary and the spin, and the shorter period ones are more likely to be detected. So yeah, there could be other things going on there that kind of tie into both observational selection effects and the uncertain evolutionary pathways. And so definitely like continuing to nail down some of the astrophysical modeling behind these systems and having more systems that we can like kind of do more sophisticated data analysis and look for some of those correlations, I think will definitely help get us a more complete picture and try to explain both the consistencies and the inconsistencies.
Cool. Very nice. Very nice. Maya, thank you so much for walking us through our fruit salad of apples and oranges. And very lovely paper. Awesome. And you touched on it a little bit there at the end. And so let me ask, where do you think we go over, let's say, the next 5 years or so? Are there additional observations that can be done? Are there new missions or telescopes coming up that can help inform this? Are there additional models that could be tried on the distributions? Are there additional theoretical calculations to be done? Just sort of, where do we head?
Yeah.
Let's say 5 years.
Yeah, all of the above. Okay. There's definitely on the gravitational wave side, like we're really making rapid progress in the detection rate. So this paper was done on 44 binary black holes. We're now up to 70 or so, just from the last half of the third observing run of LIGO, Virgo, Cagra. There's our next observing run should start like next spring. Okay. And so that will easily triple the sample of binary black holes. And so kind of thinking about learning about these astrophysical population properties of binary black holes will know so much more. On the X-ray binary side, I am less familiar with those detection prospects and missions, but I know that there are some uncertainties, like measuring the spins of black holes in those systems is pretty complicated. It requires some very sophisticated modeling. So I know that there's been a lot of progress there, and I think that is also improving. I hope that like part of this paper is to convince people that it's important that we really understand these spins in that X-ray binary system, so that we can put them together with the gravitational wave sources. But yeah, this has been an active field for a very long time, and so I think there's been a lot of progress there, and like nailing down some of those uncertainties on the modeling side, so we really have spin measurements that we trust, and even measuring like the spin misalignments, like learning about whether those spins are aligned in the X-ray binary phase can be very important. And then also on the kind of astrophysical modeling side, like we really have to understand the evolution of these systems. I mean, this is all part of this goal of learning how black holes in our universe are made. And so every step of that process leading to black holes and X-ray binaries, and then black holes and binary black holes, that's all going to both be affected by the masses and spins of those black holes, and then those evolutionary sequences may in turn affect the spins of the black holes, for example. So there's a lot of there's definitely going to be a lot of progress, I think, especially as the data set grows so dramatically at improving these evolutionary models and really trying to have the self-consistent model of like stellar evolution for massive stars leading to black holes to modeling the different mass transfer phases that we have in like X-ray binary phases to the merging binary black holes. So I think all of this is definitely coming together, and I think we should also, I'm coming from the gravitational wave side. It's been really fun to learn a little bit about the X-ray binary side, and I hope that our communities kind of continue to do that and to pull together our observations and our knowledge and come to this like big coherent picture of what these black holes are doing and where they're coming from.
Cool. I look forward to seeing this field develop over the next couple of years. I think it'll be very awesome. So thank you once again, Maya, for walking us through your very lovely paper. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.